Hi everyone, my name is Anne. I'm a third-year PhD student working on some noisy seismic data with Professor Van Derby. And over the summer, I also worked on a secondary project on some icy models with Professor Molyakova. So for my seismology project, I'm investigating this 2013 earthquake that happened in the Chicago area, right next to these major industrial operations. So the red is a limestone quarry, and the purple is a big flood control reservoir. And because of this unique location and some other factors, we believe this earthquake might have been induced by human activity. But it's really challenging to make a claim like that with just one event because earthquakes are erratic and unpredictable. So what we want to do is detect small local earthquakes that may have happened since then and compare it with local industrial activity because there's strength in numbers. But the problem is that my data is like super noisy and my noise can either hide my local earthquakes or closely resemble them. And so my broader goal is to identify waveform features that can help me better detect and discriminate events in really noisy data. And so as an example, this is a repeating signal that I see all the time. And looking at its frequency content, you can see that it's dominated by noise at this 11 Hz band. So a possible feature could be relative amplitude of this particular frequency band. It's also kind of blobby, so maybe looking at the envelope of the signal can also be helpful. And I'm also exploring some more involved features from studies in signal processing that's been promising as well. But now we'll pretend that there is a smooth transition to our secondary project. Spatial recon, and this term refers to how outshoots present massive loads on the Earth's surface, causing it to sink downward. And when that load is removed, the surface rebounds back, and this time it takes for rebound we found is proportional to the viscosity of the underlying mantle. So by comparing modeled predictions of post-glacial rebound with observations, we can get estimates of mantle viscosity, which is pretty cool. And over the years, we've gotten much better at modeling post-glacial rebound by incorporating how viscosity can vary in space, as well as other factors. But we're still seeing some major inconsistencies between our models and observed data. So what we want to do is to incorporate some recent microphysical insights, which tell us that viscosity not only changes in space, but also varies in time in some interesting oscillatory behavior, and seeing if incorporating this dimension can hopefully improve our model. And I have some preliminary results, but for time, I will skip that. But thank you for listening.
What are your preliminary results?
Well, I guess like a major inconsistency that we find is that some of our observations, the best model that we can find with a time-independent viscosity or a time-constant viscosity, can't really capture this like rapid initial rise that you see. And so incorporating some of this time varying component can a little bit better capture both the rapid rise as well as the slow tapering down. But again, very preliminary results.